Welcome, and take a slow breath as we settle into tonight's journey. We'll gently explore powerful events in the universe, not with urgency or noise, but with calm understanding. Let the vastness feel steady and quiet as we begin. A core collapse supernova begins when a massive star runs out of fuel and its iron core can no longer resist gravity. In less than a second, the core collapses inward, rebounds, and sends a shock wave outward. This shock can tear the star apart, releasing an immense burst of energy. Most of that energy leaves as neutrinos, while light and matter slowly expand into space. What remains is often a neutron star or a black hole. A Type 1a supernova occurs when a dense white dwarf undergoes runaway nuclear fusion. This happens after the white dwarf gains too much mass from a companion star or merges with another white dwarf. Carbon fusion ignites almost all at once, unbinding the star completely. No compact remnant is left behind. These explosions shine with remarkably consistent brightness. Some of the brightest explosions known are gamma-ray bursts, which release intense flashes of high-energy radiation. They can last from fractions of a second to several minutes. The energy is focused into narrow jets moving close to the speed of light. Only when a jet points toward Earth do we see the burst. Afterward, fading afterglows spread across the electromagnetic spectrum. Long gamma-ray bursts are linked to the collapse of very massive, rapidly rotating stars. As the core forms a black hole, an accretion disk feeds energy into a relativistic jet. The jet drills through the star before escaping into space. This process can also produce a supernova alongside the burst. The combination connects stellar death with extreme particle acceleration. Short gamma-ray bursts are associated with mergers of compact objects such as neutron stars. When these dense stars spiral together, they release gravitational waves before colliding. The merger ejects matter and launches jets that generate gamma rays. These events last only seconds, but release enormous power. They represent some of the most violent collisions in the universe. A neutron star merger can also produce a kilonova, a glow powered by radioactive decay. Neutron-rich matter is flung outward at high speed during the collision. As unstable nuclei decay, they heat the expanding debris. This process creates heavy elements like gold and platinum. The light fades over days as the material cools. One kilonova was observed alongside gravitational waves in 2017. This event confirmed that neutron star mergers produce both ripples in spacetime and visible light. The glow changed color as different ejector components cooled. Early emission appeared bluer, while later emission shifted to red and infrared. This observation tied together multiple messengers from one cosmic event. Some massive stars explode through pair instability supernovae. In these stars, extremely energetic photons convert into electron-positron pairs. This reduces pressure support and causes the core to contract. Explosive oxygen burning follows, which can completely destroy the star. No neutron star or black hole remains. In certain stars, pair instability happens in pulses rather than one final blast. These pulsational pair instability events eject shells of material over time. Collisions between these shells can produce long-lasting brightness. The star may survive several eruptions before its final fate. Such events reveal how unstable massive stars can be. Magnetars are neutron stars with extraordinarily strong magnetic fields. Their magnetic energy can suddenly rearrange, cracking the crust. This releases brief but intense flares of X-rays and gamma rays. Though smaller than supernovae, these flares can briefly rival distant cosmic explosions in brightness. They show how compact objects store and release energy. Some magnetar flares produce oscillations tied to the star's rotation. These oscillations reveal information about the star's interior structure. The flare energy is shaped by magnetic stresses rather than gravity or fusion. Even from across the galaxy, these outbursts can be detected. They demonstrate explosive behavior on stellar-sized objects. Tidal disruption events occur when a star wanders too close to a massive black hole. Gravitational tides stretch and tear the star apart. Part of the stellar debris falls inward and forms an accretion disk. As the material heats up, it produces a luminous flare. This reveals otherwise dormant black holes. Some tidal disruption events launch relativistic jets. When these jets are aimed toward Earth, They produce strong X-ray emission. The brightness can persist for months as debris continues to fall inward. These events bridge black hole physics and transient astronomy. They show explosions driven by gravity rather than nuclear reactions. Classical novae are surface explosions on white dwarfs. Hydrogen accumulates from a companion star until fusion ignites explosively. The blast ejects the surface layer, but leaves the white dwarf intact. Novae can repeat many times over centuries. They are smaller scale, but frequent cosmic outbursts. Gamma rays have been detected from some novae, revealing strong shocks. Faster ejecta can collide with slower material, accelerating particles. This produces high-energy emission, usually associated with much larger explosions. Novae therefore contributes to understanding particle acceleration. They show that even modest explosions can be energetic. Thermonuclear X-ray bursts occur on neutron stars in close binary systems. Accreted fuel ignites suddenly on the surface. The burst rises quickly and fades over seconds or minutes. These flashes reveal conditions under extreme gravity. They are explosive without destroying the star. Some X-ray bursts become so intense that radiation pushes the surface outward. This causes the photosphere to expand temporarily. As it settles back, the brightness changes in a predictable way. These events help measure neutron star properties. They connect nuclear physics with observable light. Superluminous supernovae shine far brighter than typical stellar explosions. Their energy can come from dense surrounding material, powerful central engines, or unusual nuclear processes. They often occur in small, low metallicity galaxies. Their light curves rise and fall slowly. These events challenge traditional supernova models. One possible engine for superluminous supernovae is a rapidly spinning magnetar. As the newborn neutron star slows down, it transfers energy to the ejector. This keeps the explosion bright for months. The process links compact object birth to large-scale light output. It shows how rotation can power explosions. Shock breakout marks the moment a supernova shock reaches the stellar surface. Photons trapped inside suddenly escape. This produces a brief flash of high-energy light. The signal can last minutes or hours. Capturing it requires constant monitoring of the sky. After a shock breakout, the star's outer layers cool as they expand. This cooling emission can be seen before radioactive decay dominates. The shape of this early light reveals the star's size. Large stars cool more slowly than compact ones. Early light curves carry information from the moment of explosion. Fast blue optical transients brighten and fade unusually quickly. They reach peak brightness in days rather than weeks. Their spectra are hot and blue early on. These events suggest small ejector masses or strong energy injection. They expand the known diversity of explosions. Some fast transients show strong X-ray and radio emission. This indicates ongoing central activity after the initial brightening. The energy source may persist rather than shutting off quickly. These observations blur the line between explosions and continuous outflows. They challenge simple classifications. Many cosmic explosions generate powerful shock waves. These shocks compress gas and amplify magnetic fields. Charged particles bounce across the shock and gain energy. This process creates cosmic rays. Explosions thus help fill galaxies with high-energy particles. Supernova remnants are the long-lived aftermath of stellar explosions. Expanding shells of gas interact with interstellar material. They glow in radio, optical, and X-ray light. Over centuries, they reshape their surroundings. Remnants preserve records of the original blast. As remnants expand, they slow down and sweep up surrounding gas. The structure becomes more uniform over time. This phase can last tens of thousands of years. Energy gradually disperses into the galaxy. The explosion's influence persists long after the light fades. Some remnants contain pulsars that continue to inject energy. The pulsar wind inflates a nebula inside the remnant. This keeps the region bright across many wavelengths. The Crab Nebula is a well-known example. It shows how explosions can have lasting engines. Historical supernovae observed by humans have modern remnants. These remnants allow astronomers to study explosions centuries later. Light echoes can even preserve information about the original spectrum. Past observations and present data combine into a fuller picture. Human records become part of astrophysics. Supernova 1987A provided an unprecedented nearby example. Neutrinos were detected before light reached Earth. Rings of gas revealed complex mass loss before explosion. The remnant continues to evolve decades later. It remains a benchmark for explosion models. Neutrinos play a central role in core collapse explosions. They carry away most of the gravitational energy. A burst of neutrinos escapes before visible light. Detecting them reveals the hidden core processes. They connect astrophysics with particle physics. Gravitational waves are produced by compact object mergers. They encode information about mass and motion. When paired with light, they form a multi-messenger signal. This allows independent distance measurements. Explosions can now be both seen and heard. Jets dominate many of the most extreme explosions. Their narrow shape focuses energy into small regions. This makes events appear brighter than they truly are. Viewing angles strongly affects observations. Geometry is as important as energy. Some explosions help measure cosmic distances. Type 1a supernovae can be standardized using their light curves. Comparing brightness and redshift reveals cosmic expansion. These explosions help discover accelerated expansion. Stellar death informs the fate of the universe. Cosmic explosions enrich galaxies with heavy elements. Oxygen, iron, and heavier nuclei are spread by blasts. These elements later form planets and life. Explosions are part of cosmic recycling. Matter is reshaped through violence and dispersal. Over billions of years, repeated explosions regulate star formation. Energy input heats and stirs interstellar gas. This prevents runaway collapse in galaxies. Explosions act as a balancing force. They shape large-scale cosmic structures. Though sudden and powerful, cosmic explosions unfold into long, quiet remnants. Energy spreads, matter cools, and motion slows. What begins in violence ends in gradual integration. The universe absorbs these events calmly. Even the largest blasts eventually settle into silence. When a massive star collapses, the structure of its outer layers strongly influences how the explosion unfolds. Stars with thick hydrogen envelopes produce long-lasting light curves, while stripped stars fade more quickly. The density profile determines how the shock loses energy as it travels outward. This is why different core collapse supernova types look so different, even when driven by similar core physics. The revival of the stalled shock in a core collapse supernova depends on neutrino heating. Neutrinos streaming from the newborn neutron star deposit a small fraction of their energy behind the shock. Even this small fraction can be enough to push the shock outward. Turbulence and convection enhance this process. Modern simulations show that three-dimensional motion is critical for successful explosions. Asymmetric explosions are common in core collapse events. These asymmetries can impart a recoil, or kick, to the newborn neutron star. Observed pulsars often move at hundreds of kilometers per second because of this effect. The asymmetry can arise from instabilities during collapse. Explosion geometry therefore affects the long-term motion of remnants. In some massive stars, rotation plays a key role in shaping the explosion. Rapid rotation can flatten the core and alter neutrino emission patterns. It can also help launch jets along the rotation axis. These effects blur the line between ordinary supernovae and jet-powered explosions. Rotation links stellar evolution to explosion morphology. Binary interaction strongly affects which explosions occur. Mass transfer can strip stars of their outer layers long before collapse. This produces hydrogen-poor supernovae such as type Ib and Ic. Binary evolution therefore increases the diversity of explosions. Many massive stars likely explode after significant interaction. Circumstellar material reflects the final years of a star's life. Dense shells indicate episodes of intense mass loss shortly before explosion. When ejecta collide with this material, shock interaction produces extra light. The resulting emission can dominate the observed brightness. These events reveal that stellar death can be preceded by instability. The chemical composition of ejecta depends on burning layers inside the star. Outer layers contain lighter elements like hydrogen and helium. Deeper layers reveal oxygen, silicon, and iron group elements. As the ejecta expands and thin, deeper layers become visible. Spectral evolution acts like a time-lapse of stellar interiors. In thermonuclear supernovae, burning proceeds through different regimes. A slow deflagration can transition into a detonation under certain conditions. The balance between these modes affects how much nickel is produced. This in turn determines peak brightness. Explosion physics directly links to observed luminosity. White dwarf composition influences thermonuclear explosions. Carbon-oxygen white dwarfs behave differently from those with significant neon. Central density affects how burning propagates. These factors contribute to subtle diversity among Type 1a supernovae. Understanding them improves distance measurements. Delayed explosions can occur in binary systems with long merger times. Two white dwarfs may orbit for billions of years before colliding. When they finally merge, conditions can ignite explosive fusion. This delay means thermonuclear supernovae trace older stellar populations. Explosion timing shapes galactic chemical evolution. Neutron star mergers depend on orbital decay through gravitational radiation. Over time, the orbit shrinks and the stars spiral together. The final seconds produce intense gravitational waves. The merger itself ejects matter and launches jets. This sequence connects slow evolution with sudden explosion. The amount of mass ejected in a neutron star merger affects the kilonova brightness. More ejecta produce a brighter and longer-lasting glow. Velocity determines how quickly the light fades. Composition sets the color by controlling opacity. Each factor leaves an imprint on the light curve. Some mergers leave behind a temporarily stable massive neutron star. This remnant can power additional winds before collapsing. These winds add material to the ejecta. The extra energy alters the observed emission. Remnant fate influences the explosion's aftermath. Black hole neutron star mergers produce different signatures. If the neutron star is swallowed whole, little light is produced. If it is torn apart first, a kilonova can still occur. The outcome depends on mass ratio and spin. Explosion visibility varies with merger geometry. In collapses, accretion rate controls jet power. Higher rates feed stronger jets. As the star collapses, the disk evolves rapidly. Variability in the engine produces variability in gamma-ray emission. The burst records the behavior of infalling matter. Jet breakout from a star deposits energy into surrounding material. This forms a hot cocoon that can radiate independently. Cocoon emission may be visible even when the jet is misaligned. It provides clues to jet formation. Breakout physics links stellar structure to observed transients. After a gamma-ray burst, the afterglow traces jet deceleration. As the jet sweeps up external gas, it slows down. Emission shifts to longer wavelengths over time. The afterglow can last months or years in radio bands. This phase maps the surrounding environment. The density of the circumburst medium shapes afterglow evolution. Dense environments produce brighter, faster fading afterglows. Low-density regions yield slower evolution. Measuring this helps infer where the explosion occurred. The environment ties explosions to their host galaxies. Magnetar-powered explosions depend on spin-down timescales. Faster initial rotation injects energy more quickly. Slower spin-down extends luminosity over longer periods. Magnetic field strength controls the rate of energy loss. Compact object properties determine large-scale light curves. In superluminous supernovae, ejecta mass can exceed that of typical explosions. Large mass slows expansion and prolongs brightness. This leads to broad, smooth light curves. The scale suggests very massive progenitors. Such explosions probe extreme stellar evolution. Pair instability explosions leave distinct nucleosynthetic signatures. They produce large amounts of intermediate mass elements. Iron group elements may be less abundant than in other supernovae. These patterns can be searched for in old stars. Chemical fossils test explosion theories. Pulsational pair instability events reshape the progenitor before final collapse. Each pulse removes mass and alters the envelope. The final explosion interacts with previously ejected shells. This layered structure produces complex light curves. Pre-explosion history matters greatly. Shock interaction converts kinetic energy into radiation efficiently. When fast ejecta hit dense material, shocks heat gas strongly. Radiation escapes as optical, X-ray, and radio light. This process can dominate luminosity. It shows how the environment amplifies explosions. Radio emission often traces long-term shock evolution. As shocks propagate, they accelerate electrons. These electrons emit synchrotron radiation. Radio light can persist long after optical emission fades. It provides a durable record of explosion energy. X-ray emission reveals high-temperature shocked gas. Temperatures can reach millions of degrees. This emission probes shock speed and density. X-rays penetrate dust that blocks optical light. They offer a clearer view of hidden regions. Dust formation occurs in cooling ejecta. As temperatures drop, atoms condense into grains. These grains can survive or be destroyed by later shocks. Supernovae thus both create and process dust. Dust influences future star and planet formation. Fallback accretion can modify explosion outcomes. Material that fails to escape falls back onto the remnant. This can increase remnant mass or power late emission. In extreme cases, it leads to black hole formation. Explosion strength determines how much material escapes. Failed supernovae may produce little visible light. The star collapses quietly into a black hole. Only subtle signals, such as disappearing stars, reveal the event. These outcomes show that not all stellar deaths are bright. Silence can follow collapse. Electron capture supernovae occur in a narrow mass range. Their cores collapse when electron pressure suddenly drops. Explosion energy is relatively low. These events may explain some faint supernovae. They highlight alternative collapse pathways. Time domain surveys have transformed explosion studies. Repeated scans of the sky catch events early. Early detection reveals initial conditions. This improves modeling of formation and evolution. Observation cadence shapes scientific insight. Large statistical samples reveal population trends. Rates of explosions vary with galaxy type and star formation rate. These trends link explosions to stellar demographics. Population studies test theoretical predictions. They turn individual events into cosmic statistics. Cosmic explosions influence galaxy evolution through feedback. Energy injection heats gas and drives winds. These winds can escape small galaxies. This regulates future star formation. Explosions help set galaxy-scale properties. Over cosmic time, explosion rates evolve. Early galaxies experienced more massive star explosions. Later times see increased contribution from delayed events. This evolution shapes chemical abundances. The history of explosions is written into stars. By studying formation and evolution, cosmic explosions become structured rather than chaotic. Each stage follows physical laws. Initial conditions shape outcomes. Energy disperses in predictable ways. Even the most violent events obey calm patterns of physics. At the smallest scales, nuclear reactions inside exploding stars govern how energy is released. Fusion chains proceed through precise reaction pathways determined by temperature and density. Slight changes in reaction rates can alter which elements are produced. These microscopic processes scale up to shape the entire explosion. Stellar explosions therefore connect nuclear physics directly to cosmic structure. Radioactive decay plays a central role in powering many explosive light curves. Unstable isotopes such as nickel-56 decay into cobalt-56, and then iron-56. Each decay releases gamma rays and particles that heat the ejecta. As the material expands, this energy is converted into visible light. The timing of decay sets how brightness rises and falls. Gamma rays produced inside ejecta do not escape immediately. Early on, dense material traps high-energy photons. As expansion continues, the ejecta becomes transparent. The changing escape fraction alters how energy is deposited. This gradual transparency shapes late-time light curves. Atomic transitions determine the detailed appearance of spectra. Each element absorbs and emits light at characteristic wavelengths. As temperature and density evolve, different ions dominate. This produces shifting spectral lines over time. Spectroscopy acts as a fingerprint of explosion chemistry. Line broadening in spectra reflects ejecta velocity. Faster expansion spreads absorption features over wider wavelength ranges. Measuring this broadening reveals kinetic energy. Changes over time track deceleration. Velocity information is encoded in light. Polarization measurements probe explosion geometry. If ejecta were perfectly spherical, polarization would cancel out. Detected polarization indicates asymmetry. Different wavelengths probe different depths. Polarimetry reveals three-dimensional structure from distant points of light. Shock fronts compress and heat gas on microscopic scales. Particle collisions transfer energy rapidly. Electrons and ions can reach different temperatures. Equilibration occurs over time through collisions. These microphysics affect emitted radiation. Collisionless shocks rely on electromagnetic interactions rather than direct particle collisions. Plasma instabilities mediate energy transfer. These processes dominate in supernova remnants. They allow efficient particle acceleration. Microphysics governs cosmic ray production. Magnetic field amplification occurs at shocks through turbulence. Small seed fields grow rapidly. Stronger fields enhance synchrotron radiation. This changes radio and X-ray brightness. Magnetic microphysics shapes macroscopic emission. Synchrotron radiation arises when charged particles spiral in magnetic fields. The emitted spectrum depends on particle energy distribution. Measuring spectral slopes reveals acceleration efficiency. Synchrotron cooling also limits particle lifetimes. This emission links particle motion to observed light. Inverse Compton scattering transfers energy from fast electrons to photons. Low-energy photons gain energy through collisions. This produces high-energy emission. The balance between synchrotron and inverse Compton processes depends on the environment. Small-scale interactions control broadband spectra. Neutrino interactions inside collapsing cores influence explosion viability. Neutrinos scatter off nucleons, depositing energy. Cross-sections depend on particle physics parameters. Flavor transformations alter interaction rates. Fundamental particles affect stellar death. Neutrino oscillations can change flavor composition. As neutrinos escape, matter density affects oscillation behavior. These effects imprint subtle signatures on detected signals. Observations can probe both supernova interiors and neutrino properties. Astrophysics becomes a particle experiment. Gravitational wave emission encodes motion of dense matter. Tiny distortions in space-time propagate outward. Detectors measure changes smaller than atomic nuclei. Signal shape reflects mass and orbit. Microscopic precision reveals macroscopic violence. Waveform modeling requires relativistic calculations. General relativity governs the motion. Numerical simulations track inspiration and merger. Small numerical errors matter greatly. Precision theory is required to decode signals. Detector sensitivity depends on noise control. Thermal, seismic, and quantum noise must be reduced. Advanced engineering enables detection. Instrument physics underpins astrophysical discovery. Quiet laboratories reveal cosmic explosions. Timing accuracy is critical in multi-messenger astronomy. Comparing arrival times constrains physical processes. Millisecond differences matter. Precise clocks synchronize observatories. Coordination turns events into detailed experiments. High-energy photons interact with interstellar matter. Absorption lines reveal intervening gas. Dust scattering alters spectra. Correcting for these effects requires atomic data. Line-of-sight physics shapes observations. Opacity in ejecta depends on atomic structure. Heavy elements with many electrons have complex line forests. These increase opacity. Higher opacity traps radiation longer. Microscopic atomic physics affects macroscopic brightness. Dust grains absorb and re-emit light. Grain size and composition determine wavelength dependence. Infrared emission traces dust formation. Destruction by shocks alters grain populations. Solid-state physics enters explosion studies. Ionization states change as radiation fields evolve. Photoionization competes with recombination. Balance depends on density and temperature. Spectral diagnostics track these changes. Plasma physics shapes observed spectra. Cooling processes govern how fast ejecta lose energy. Radiative cooling competes with expansion. Different elements cool efficiently at different temperatures. Cooling curves influence remnant evolution. Energy loss pathways matter. Hydrodynamic instabilities grow from small perturbations. Rayleigh-Taylor instabilities mix layers. Kelvin-Helmholtz instabilities shear material. Small initial differences grow large. Chaos amplifies microscopic variations. Numerical simulations must resolve many scales simultaneously. Grid resolution affects instability growth. Subgrid models approximate unresolved physics. Computational choices influence outcomes. Simulation accuracy underpins interpretation. Atomic databases provide transition probabilities and collision rates. These data are essential for modeling spectra. Laboratory measurements inform astrophysical models. Precision data enable accurate abundance estimates. Earth-based experiments support cosmic studies. Cosmic ray propagation depends on scattering off magnetic irregularities. Small-scale turbulence controls diffusion. Energy losses shape spectra. Modeling requires plasma microphysics. Galactic radiation backgrounds are influenced by explosions. Radioactive isotopes emit characteristic gamma-ray lines. Detecting these lines reveals nucleosynthesis directly. Line strengths trace isotope abundance. This bypasses some modeling uncertainties. Gamma-ray spectroscopy probes explosion interiors. Time resolution matters in capturing rapid phases. Millisecond scale variability can reveal engine behavior. Instrument readout speed limits detection. Faster sampling uncovers finer structure. Temporal microphysics become visible. Spectral resolution determines line identification. Blended lines obscure details. Higher resolution separates components. This improves abundance measurements. Instrument design shapes scientific return. Calibration stability affects long-term monitoring. Small drifts can mimic physical changes. Careful calibration ensures reliability. Precision measurement requires constant vigilance. Instrument physics supports astrophysics. Statistical uncertainties shrink with repeated observations. Noise averaging reveals faint signals. Data processing extracts weak features. Statistical methods underpin discovery. Mathematics joins physics. Machine learning now assists transient classification. Algorithms detect subtle patterns. Training data encode prior knowledge. Automation speeds discovery. Computational techniques influence detection. Laboratory nuclear experiments constrain reaction rates. Measurements reduce uncertainty in models. Improved rates refine explosion predictions. Terrestrial experiments inform cosmic explosions. Cross-disciplinary work advances understanding. At the smallest scales, every cosmic explosion is a sum of countless particle interactions. Each collision, decay, and transition contributes. Together they build the light we see. Vast displays arise from tiny processes. Complexity resolves into quiet physical law. As the light from a cosmic explosion fades, what remains is often a slowly expanding cloud of matter that continues to interact with its surroundings. Over years and centuries, the expansion becomes gentler, and the initial violence is remembered only through motion and composition. The remnant carries energy outward in a steady, predictable way. This gradual evolution shows how sudden events transition into long-term structure. The universe absorbs explosions patiently. Supernova remnants eventually merge with the interstellar medium. Their distinct boundaries soften as shock speeds decrease. Temperature differences even out over time. What was once a clearly defined shell becomes part of the larger galactic environment. Matter returns to a shared cosmic cycle. The heavy elements produced in explosions slowly mix into surrounding gas. Turbulence spreads them through molecular clouds. Over millions of years, these enriched regions can form new stars. Planets inherit material forged in earlier explosions. Creation follows destruction on long timescales. Energy injected by explosions dissipates gradually. Turbulent motion converts ordered kinetic energy into heat. Radiation carries energy away into space. Nothing remains concentrated forever. The universe trends toward balance after disruption. Some remnants remain visible for tens of thousands of years. Their glow slowly dims as particles lose energy. Radio emission can persist the longest. Even so, each remnant eventually fades below detectability. Time gently erases sharp signatures. Neutron stars left behind cool steadily. Heat from formation radiates away through neutrinos and photons. Rotation slows as energy is lost. Magnetic fields decay over long periods. The compact object settles into quiet persistence. Black holes formed in explosions are silent by nature. Without surrounding matter, they emit no light. Their presence is inferred only through gravity. They remain as calm endpoints of violent beginnings. Stillness follows collapse. In merger events, debris spreads into elongated streams, Over time, these streams circularize or disperse. Gravitational interactions smooth their structure. The dramatic collision gives way to orbital calm. Order re-emerges through dynamics. Kilonovae ejecta expand and cool rapidly. Radioactive heating weakens as unstable nuclei decay away. After weeks, little light remains. The matter continues outward unseen. Heavy elements drift silently through space. Jets from gamma-ray burst slow as they encounter resistance. Relativistic motion becomes sub-relativistic. Emission shifts to longer wavelengths. Eventually, the jet material blends with ambient gas. Directional violence becomes isotropic calm. Afterglows fade in a predictable sequence. X-rays dim first, then optical light, then radio. Each band traces a different physical process. Observations gradually cease. The sky returns to its prior quiet. Magnetar flare remnants disperse quickly. The intense radiation pulse passes, leaving little trace. Only long-term monitoring reveals changes in spin or magnetic field. The star resumes a quieter state. Activity becomes sporadic again. Tidal disruption debris can settle into long-lived disks. Accretion rates decline smoothly. Luminosity decreases over months to years. The black hole returns to dormancy. The event becomes a memory recorded in data. Nova shells expand gently after their initial burst. They cool and thin, becoming transparent. Eventually, they are indistinguishable from surrounding gas. The white dwarf resumes accretion. The cycle prepares for another outburst. X-ray burst ashes sink into neutron star crusts. Nuclear byproducts alter crust composition. Over time, the surface resets. Bursts recur under similar conditions. Repetition brings familiarity. Superluminous supernova remnants may leave unusually massive shells. These shells take longer to slow. Their influence extends farther into space. Even so, gravity and pressure guide them toward equilibrium. Extremes relax with time. Shock-heated gas cools through radiation and expansion. Cooling lines appear as temperatures drop. Emission shifts from X-rays to optical wavelengths. Eventually, emission becomes faint. Energy dispersal completes its course. Dust formed in explosions drifts through space. Some grains survive intact. Others are destroyed by later shocks. Surviving dust joins molecular clouds. Solid matter quietly contributes to future systems. Cosmic rays accelerated by explosions diffuse away. Their energies decrease through interactions. They fill galaxies uniformly over time. Local enhancements fade. High-energy traces smooth out. Gravitational waves pass through the universe without resistance. After they pass, space-time returns to its prior shape. No permanent disturbance remains. The signal exists only as a fleeting ripple. Silence follows vibration. Neutrinos escape explosions almost immediately. They rarely interact afterward. Once gone, they leave no local trace. Their passage is brief and gentle. Even powerful processes release quiet messengers. Observationally, attention shifts from explosion to context. Host galaxies are studied. Star formation environments are examined. The event becomes part of a larger picture. Focus widens as intensity fades. Archival data preserve explosions long after light fades. Measurements remain available for reinterpretation. New theories revisit old events. Knowledge continues to grow quietly. Discovery extends beyond observation. Statistical studies smooth individual differences. Patterns emerge from many events. Extremes average into trends. Understanding becomes calmer and more complete. Chaos resolves into order. The universe does not rush to erase explosions. It allows them to settle naturally. Time acts as a stabilizing force. Change proceeds without urgency. Calm follows intensity. From a distance, explosions are brief interruptions in cosmic continuity. Most of the space remains unchanged. Vast regions experience no disturbance. The overall universe remains steady. Events are local, not universal. Even the most energetic explosions affect only limited volumes. Beyond that, space remains quiet. Galaxies continue their slow rotation. Stars evolve at their own pace. Balance dominates scale. As centuries pass, remnants become teaching tools rather than spectacles. They inform models and refine theory. Their beauty becomes subtle. Attention shifts from brightness to meaning. Reflection replaces astonishment. The cycle of stellar birth and death continues without pause. Explosions are transitions, not endings. Matter moves from one form to another. Continuity persists through change. The cosmos remains patient. In the longest view, explosions contribute to stability. They regulate star formation. They distribute elements evenly. They prevent extremes. Order emerges from disruption. Understanding cosmic explosions becomes an act of quiet comprehension. Equations replace surprise. Patterns replace unpredictability. Knowledge grows steadily. Wonder softens into familiarity. What once appeared violent becomes understood as necessary motion. Energy flows according to law. Matter follows predictable paths. The universe behaves consistently. Calm explanation replaces mystery. As attention drifts outward, individual explosions lose prominence. The larger structure of the cosmos takes focus. Scale dwarfs intensity. Perspective brings peace. Vastness absorbs detail. In the end, cosmic explosions are moments within a much longer story. They rise, peak, and fade. What remains is continuity. Space settles back into stillness. The universe carries on, quietly and endlessly.